Addis, and I'd like to welcome you to today's Addis webinar on GPS vulnerabilities and implications for telecom. Before we get started, I'm going to take just a few minutes to explain some features of today's webinar. This presentation is being recorded, and you are currently in listen-only mode. We encourage you to submit questions at any time during the program. If you have a question, first locate the question box in the upper right-hand corner of your screen. Next, enter your question in the text box and click Send. We'll hold all your questions until the end of the presentation and then answer as many questions as time permits. Our speakers will discuss telecom systems dependence on GPS and GNSS and provide insight into the options for backing up these systems using holdover and alternative time transfer techniques. On behalf of Addis, I'd like to thank our speakers for today, as well as NIST for their collaboration with us to bring this webinar to you. Without further delay, I am delighted to introduce today's moderator, Dr. James Armstrong. James joined Telecom in 2006 and currently serves as Telecom's Chief Technology Officer. He is also a member of Addis's Board of Directors. And now, James, let me turn the floor over to you.
Thank you, Lauren. Our presenters today are Dr. Todd Humphreys. He is an assistant professor in the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin and director of the University of Texas Radio Navigation Laboratory. His recent focus is on radio navigation robustness and security. Our other presenter today is Dr. Martin Nuss. He joined Vitesse in November of 2007 as Vice President of Technology and Strategy and Chief Technology Officer. Mr. Nuss is a Fellow of the Optical Society of America and a member of IEEE. Todd and Martin, thank you for joining us today. I will start with a few slides just to tee up the topic for today and give a quick overview. As we all know, GNSS is a technology that is used, is deeply embedded in the infrastructure of our various countries around the world, from communications, and that's the primary focus of today's discussion, and we're focused primarily on the wireless portion of communications, but we know that the legacy network, the TDM network, is highly dependent upon synchronization, and that synchronization originates with typically a GNSS feed. Power utility also, there's phasor alignments that need to be in place in order to merge two sources of power together and phase align them, and GNSS is used in that capacity, as well as for time stamping for error correction and traceability of errors, and so GNSS is used pervasively in the power utility market, and I believe Todd will be touching more on that. Throughout defense, we know GNSS is used for positioning. We know through navigation for the arms and munitions and so forth, tracking all the assets. GNSS is used pervasively there. Information technology and for time stamping and tracking and for being able to recreate errors and understand what's happened in the light of errors. Time stamping is used very precisely in information technology, as well as in enterprises. We'll hear more about the high-frequency trading application, which demands very tight timing and synchronization, and that typically comes from GNSS. And there's a number of other applications here. I don't want to go through them all in this process. We know that through agriculture and other things, very dependent upon GNSS to track assets and so forth. So GNSS is something that is used pervasively in our society for precise synchronization, for navigation, and positioning. Just please turn to the next slide. So here's a study that was done a few years back, and it's just a glimpse of these notice to airmen, which is a message that goes out to the airports and the aviation groups about where GPS is anticipated to have an outage. And usually that's driven by the government running some kind of, in particular, defense running some kind of trial of some sort, and they may be jamming GPS in those areas. And this is a picture of it. And if you just do a simple calculation and you look at the average square miles that the event takes place in, and you look at the duration of that event, and it's over a 9-month period that this study was taken, and you know the square, you know the area of the United States, you could conclude, you know, in a very simplistic form that GPS is, you know, is available 99.6% of the time. And when you build equipment that depends on GPS, you don't know where that equipment is going to be installed. And as you can tell here, there's certain areas of the country that might be more vulnerable to these kind of trials and exercises that the government is doing. And so you don't know if you're going to be in one of those areas where when that piece of equipment is deployed, so you have to protect against it. If you please go to the next slide. And there's another, and added to just the typical type of government exercises that happen that might jam GPS, there's a lot of localized type of incidences that may interfere with GPS. And here is the first picture here is a little portable GPS jammer. And those GPS jammers are not illegal to own, but they're illegal to use. And so those things, they just plug into your car, into the car lighter, and it could jam GPS within the 300-meter radius around. And that's been known to interfere with cell sites, been known to interfere with the GPS at airports, and they seem to be growing in use. And so jamming and spoofing we'll hear more about from Todd, and he kind of covers that in specifics. But we see that as a growing area of disturbance to GNSS, and so that's a concern. But then we also have the typical mechanical failures. You have this antenna that's up there. It's subject to vandalism, and so, and in addition, just normal wear and tear from trees and other things, branches falling on it or hitting them, and so there's typical mechanical failures that could occur. And in addition to that, you have the standard environmental and storm conditions that could create outages of GPS temporarily. So in addition to the broader type of, I would say, mass type of outages that the Department of Defense could cause in specific exercises and so forth that it undertakes, there are localized events that add to the vulnerabilities and to the jamming of GPS that impacts the reliability of GPS. And so that's something that is of growing concern, and that's the subject of today's discussion. Now, particularly for telecom, and one of the fastest growing areas of telecom is obviously mobile communications. So if you please go to the next slide, mobile communications is highly dependent upon synchronization among the base stations. So two base stations, they'll have overlapping areas that they serve in terms of their service area, and those two base stations need to be synchronized to a certain degree of accuracy. Now, all the mobile technologies require some form of synchronization. Some of them require frequency synchronization. That means the frequency that they're synchronized in frequency to base stations in some cases. In other technologies, it requires not only frequency, but it requires a phase. That means the leading edge of a pulse has to be aligned with the leading edge of a pulse on another base station with a certain degree of accuracy. And so you can see here that in certain forms of LTE, for example, the FDD, which is the frequency division duplex form of it, it's frequency synchronization. But as you move into more of the advanced service, where it's time division duplex, it requires phase synchronization. CDMA requires phase synchronization. And these phase requirements are even more stringent, more difficult to accomplish than the frequency requirements. So these are very tight requirements. Typically, GPS in the past has been used to meet these type requirements, or any form of GPS. GNSS is GPS, I should say, is a subset of GNSS. GNSS is a global navigation satellite system. One form of that, one version of that is GPS. The oldest version of that is GPS. And so GNSS is a general term for that. So GNSS has been used to meet these very tight timing requirements for the mobile rollout. And so when GPS is not there, or if it's increasingly more vulnerable, it has a severe impact to the mobile infrastructure. And we'll go to the next slide, kind of describe some of the things that you'd experience if you don't have the synchronization there between between two base stations. So for the different technologies, the effect is different. So for LTE, in terms of the FDD version of LTE, the frequency-based version of LTE, if you don't have two base stations that are synchronized to a certain degree of accuracy and frequency, then call handoff doesn't happen. So if you're driving down the road, you're on a call, you're connected to one base station, typically you get handed off to another base station as you go along, and it's seamless. That's only if the two base stations are synchronized in frequency to a certain degree of accuracy. For LTE, TDD, and some of the more advanced forms of LTE, it requires phase-accurate synchronization. And if you don't get that phase-accurate synchronization, then what happens is your performance is degraded significantly. So you're deploying these small cells that are out there. You want to have higher bandwidth in terms of the technology. The reason why you're deploying this, you want to increase your bandwidth. Well, if you don't have the right level of synchronization, if you don't meet the requirements in the synchronization requirements that are for that technology, then you have to roll back to technology, to versions of that LTE technology that doesn't achieve that kind of performance. So all that expenditure to roll that out will not be achieved unless you have that level of synchronization. And so you could take a look at here as some of the things that might impact it. You know, here are the specs for these different technologies for LTE and the type of impact that it might have if you don't achieve that. So that's just something, I don't want to get into too much detail, but it's something that they do have a very significant impact on these technologies. So the way, so there's different technologies that are out there to synchronize. If you go to the next slide, there are different technologies that are out there that are being used in order to overcome potential vulnerabilities in GPS. And certainly GNSS is a very prevalent form of timing technology used for the mobile applications, and it will continue to be. It is pervasive in the areas. It is a very accurate form of synchronization as well when it's present. And so the challenge here is, how do you fill the gaps when it's not present? And so there's other technologies that are out there that are being now used in conjunction with GNSS to make the whole solution more reliable. So we have some network-based timing technologies. IEEE 1588 has been recently ratified, and that's being deployed now as a form of synchronization for base stations. We also see synchronous Ethernet, which is really building in at the physical layer frequency timing, frequency synchronization along the line. It actually is very similar to the E1T1 type of synchronization that is passed down to base stations, that many base stations use to synchronize themselves in terms of frequency. Now, as you increase the bandwidth that you need to backhaul the data and the voice that's coming across the mobile technologies, it's really cost prohibitive to continue to deploy E1T1, so Ethernet's being deployed, but that typical Ethernet, native Ethernet, does not have physical layer synchronization. So synchronous Ethernet was something that was recently ratified as well in the standards body in order to, at the physical layer, to pass some kind of synchronous feed down, because these base stations require such accurate synchronization. So 1588 is one form, synchronous Ethernet is another form, and then if none of those are available, or if the type of network is not conducive to those forms of timing technology, the oscillator is used to hold over the gaps when GNSS reception isn't there. So rubidium is an atomic technology in order to really meet those tight timing requirements for advanced LTE and the phase requirements. It looks like the rubidium type of technologies, the atomic technologies for oscillators, are ones that could hold that for the amount of time that you could get service to that location and so forth. And so that's an option to use in order to back up GNSS. So what you see out there, because of the criticality of the mobile infrastructure, the growing criticality really, and the importance of synchronization and timing, which typically originates with GNSS, but we know there's increased issues with GNSS, as I mentioned before. A combination of these technologies are being used in order to provide a reliable and accurate solution. And Martin will also discuss later 1588 and some of the performance that he's seeing with 1588, and it's improving all the time. So these are the technologies out there, and we'll like to discuss how some of these technologies are used, and we also like to discuss a little bit more about some of the vulnerabilities that we see in GNSS. So without further ado, I'd like to be able to turn this over to our next presenter, who is Todd Humphreys. Todd? Todd, are you there?
James, I think we're having some technical difficulty with Todd's line. Could we jump right into Martin's presentation and then come back to Todd?
Sure. So we'll move over to Martin's presentation, and he will talk to us about network timing.